Hi, in this chapter, we're going to go through some of the popular search and sort algorithms. So in this chapter, we'll first talk about algorithms, and then we're going to talk about the linear search and binary search. Those are the two search algorithms that we have in this chapter. And finally, we're going to talk about three different sort algorithms, namely the selection sort, bubble sort, and the quicksort. So we all know what an algorithm is. An algorithm is a set of steps which accepts some set of values as input and produces a set of values as output. Now for a given problem, it's not necessary that we're going to have just one algorithm. You can have multiple algorithms to solve the same problem. And the algorithm you would generally pick is the one that executes the fastest. So you say a particular algorithm is a good algorithm or a good solution when that algorithm is better than the others in either occupying less space or is faster in execution time. We shall first take a look at the linear search algorithm. A search algorithm is one where, given a set of numbers, the algorithm has to search for a particular number. So you'll be given an array with a lot of numbers and a key element that you want to search for, and the algorithm has to search for that element or that number and return its position. So there are multiple ways of implementing a search algorithm. We shall first talk about the linear search. The linear search is the simplest algorithm for searching. That's because it's very similar to how you would search for a number given a set of numbers. Let's see how the linear search algorithm works. So let's say our array has about 5 elements or 5 numbers. So I'm going to have 25, 46, 10, 5, 14. And I want to search for the number 5. So how do we go about doing it? Manually, if you're asked to search for the number 5, of course, there are just 5 numbers. You can easily see this is where 5 is. So it's in the position number 0, 1, 2, 3. Position number 3. That's because it's right in front of your eyes. But let's say you had 100 numbers. How do you go about searching? You'll start with the first number. You'll say, is this 5? No. Is this 5? No. Is this 5? No. Is this 5? Yes. And you will stop here. That is how the linear search works too. When you have to write a program for it, you start from the first number. Keep verifying if this is the number you're searching for. No. Go to the next one. No. No. Finally, you found it. And then you return this position, that is 0, 1, 2, 3. You'll return the position 3. Let's say you're searching for the number 50. Then we start searching. 25, no. 46, no. 10, no. 5, no. 14, no. We've reached the end of the list and we haven't found it. So we just return -1, which means we couldn't find the element. Simple, right? So if you take a look at the algorithm too, it's the same thing. For each element in the array, check if the element is equal to the key we're searching for. If it's equal, then return the location of the element. Now let's write a program to do the same. We first start with our hash include. Now the function, let's call it linear search. This function has to return a number to us, so it's going to return an integer. The number can be either -1 if it did not find the key, or it would be the position of the number. The other input is, the first input is the array. So int a, or let's just say int star a. Then the key element we're searching for, int key. And like I said, in any given array, we don't know the size of the array. So instead of taking the size here, we're going to accept the starting index to start searching from and the last index to stop searching. So let's say int imin, comma int imax. So we're going to start searching from imin, go up to imax, which means let's say we have 10 elements in the array and we want to search through the entire array. Imin will be 0 and imax will be 9. So you'll search from 0 to 9. Okay, so how do we go about doing the linear search? We need a for loop. We need to go through every element. So int I, for I starts from imin, I stops at imax, keep incrementing I. What do you do in the for loop? You check if a of I is equal to key. Key is the element we're searching for. So right now we are the ith element. We're checking if a of I is equal to key. If that's the case, we just return I. Now if we come out of the for loop, means we did not find the key. So we can just say return -1. That's our linear search function. Now let's write the main. We first need to declare the array. But in this case, we're not going to use a static array. We're not going to assume that the user is going to enter 10 numbers or 5 numbers. None of that. We're going to ask the user first as to how many numbers he wants to enter. And then he's going to enter the numbers. So we're just going to have a empty pointer first, star arr. So you can just say equal to null. It's not pointing to anything. We then ask the user printf how many numbers scanf %d ampersand num. So we need a num int num. So we accepted num from the user. Now we need to allocate space for num integers. So arr is equal to int star malloc num into size of int. So we've allocated space. Now we can start accepting the numbers from the user. Say printf enter the numbers for I equals 0, I less than num I plus plus scanf %d comma ampersand a of I. So as you can see here, arr is a pointer, but we're using it like an array because, like I said earlier in one of the chapters, arrays and pointers can be used in a similar way. So when I use arr of index, the calculation is similar to saying arr plus I. So you can just say arr of I2. So we have accepted all the numbers from the user in the for loop. Now we have to search for a particular element. So let's ask the user to enter which key to search for. So printf enter the search key scanf %d. Let's call the variable key. So we need an int key. And finally, now we call linear search to search for that. So linear search, we have to pass the array of the pointer, then the key. Then we need to start searching from 0 to num. But it's not 0 to num, it will be num -1. That's because if we have num as 10, the index is actually from 0 to 9. So you always pass 1 less. And finally, linear search will return either -1 or the location. So let's have it as loc equals this. So we need another variable. If loc is equal to -1, printf key not found, else if it's any other number, printf key found at position %d. loc +1. This is because, let's say the number we're searching for is the first number. The function linear search will return 0 to us because that's the 0th index. But to the user, it's always nice to show it as 1 because that's the first number. If it's second, we show it as 2. So we always increment it by 1. Finally, system pause and return 0. Let's now compile our program. We have an error. It says I undeclared. So we're using I here, we have not declared I. Let's compile it again. No errors or warnings. Let's run it. Enter how many numbers? Let's say 5 numbers. Enter the numbers. So I'm going to say 25, 10, 46, 100, and 5. Enter the search key. Let's say I want to search for the number 100. 100 is the position 1, 2, 3, 4, the 4th position. And we have a problem. So as you saw, the program quit abruptly. That's because we had a segmentation fault. That is when such things happen, when you're trying to access a wrong memory location. So let's just look at our program. You can see over here we're doing scanf and we're not passing the address of key, passing key itself. So whatever value we entered for key was being stored at a wrong address which does not even belong to us. Let's compile and run this again. How many numbers? 5. Enter the numbers 46, 25, 50, 100, 10. Searching for the number 100. Key found at position 4. Let's try again and search for something that doesn't exist. 5 numbers, 1, 2, 3, 4, 5. Let's search for 6. Key not found. Now let's see if there's a way to make this algorithm faster. This was the array in the example that we had spoken earlier. As you can see, the numbers are not in sorted order, and if I'm searching for a particular number, I have to search every element. There is no way I know where the number could be, so I have to start searching from here, go one by one till I find it. But can I make a search algorithm faster if the numbers were already sorted? So let's say I had the numbers like 10, 15, 18, 100, 250. So the number is sorted in ascending order. In this case, if I'm searching for the number 250, what does the linear search do? We'll start here. No, 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 yes. So it's going to go through the loop 1, 2, 3, 4, 5 times. If there are 100 numbers and the number we're searching for is in the 67th position, then it's going to iterate through the loop 67 times. Can we reduce this number? Do we really need to go through the loop 67 times? Let's look at a new algorithm which works on sorted arrays. This is called binary search. It takes advantage of the fact that the array is already sorted. So once we have a sorted array, we don't have to actually go through every element starting from the first one. Let's see how binary search works. So let's take a few numbers and it's going to be sorted. So let's say 5, 10, 20, 45, 100, 115. So we have a proper sorted list, and let's say I'm searching for the number 100. If it was a linear search, what we would have done is start from here. No, 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 yes. So it's 1, 2, 3, 4, 5. We would have gone through the for loop 5 times till we found the key we are searching for. What binary search algorithm says is that split your list in half. Find the middle element first. So how many elements do we have? 1, 2, 3, 4, 5, 6. So 6 by 2 is 3. So you go to the third element. Is this the number we're searching for? No. But now we know that the array is sorted. So you can check if the number you're searching for is greater than this number or not. If it's greater, we know the number will be only over here. If it's less than this number, then the number will be somewhere here. So is 100 greater than 20? Yes. That means we know the number is somewhere in this half of the array. So next we need to only search this stretch. So we need to only search this half. So now we assume this is a subarray. Again, we repeat the same binary search algorithm. We have 3 elements, was 3 by 2, 1.5, which means, let's say it's 1, because in integers you're going to round it off. First element, we're going to search here. Is this the one we're looking for? No. Now the number you're searching for, is it greater than 45? Yes. That means it's going to be in this half. Now again we take these two. 2 by 2 is 1. So search, is this the first element? Is this the number we're looking for? Yes. And we found it. So how many times did we have to actually do the search, or how many times did we have to go through the loop? We first checked against 20, that's 1. Then we checked against 45, that's 2. Then we checked against 100 and we found it. That's 3 times. So already for 5 numbers, instead of going through the loop 5 times, we went through it 3 times. So if you have 100 or 1000 numbers, the average case for a binary search is much faster than the linear search. So let's just look at the algorithm. The algorithm is similar. Pick the middle index, imid, of the array. If the element at imid is equal to the key we are searching for, then we return that index. If the key is less than the element at the middle, then repeat the process for the subarray from imid till the middle element, that's imid minus 1. If the key is greater, then we repeat the process for the subarray imid plus 1 till imax. Let's go ahead and write a program for this now. So let's start with our hash include. Next, our binary search is going to be similar to the linear search as far as the function declaration goes. So int, let's call it binary search. It needs an array as input too. It needs the key we're searching for. Then you need the imin and the imax, that's the starting index and the ending index. Okay, so what do we need to do in the binary search? We first need to calculate the middle index. So let's have int imid. Imid is equal to imin plus imax divided by 2. Once we've calculated the imid, we need to check if that is a key element that we're searching for. A of imid is equal to key. If that's the case, we return imid. If that's not true, then we need to check if key is greater than a of imid. Key is greater than a of imid. Then what do we need to do? If key is greater, that means we need to search in the right half. So we need to search from imid plus 1 to imax. So which means imin becomes imid plus 1. So we say imin is equal to imid plus 1. Because we're always searching for imin to imax. So we first start from 0 to, let's say, 10. 0 to 9, that is. And we found that the middle element is smaller than key. So key has to exist in the right half. So imin becomes imid plus 1. We again search from imin to imax. We shall keep repeating this loop. We'll see how. Finally, else. You don't need an if over here because key is not equal to a of imid, or it's not greater than, that means it is less than. So we can say else imax equal to imid minus 1. Again, we return the loop from, we run the loop from imin to imax. So now we need to repeat this thing in a loop How many times? We don't know how many times, right? But we know one thing, that at every point, either Imin gets incremented or Imax gets decremented. That means at some point, Imin and Imax will be the same, or Imax will be less than Imin. So this loop stops when Imin is greater than Imax. So it means we need to keep repeating this while Imin is less than equal to Imax. So we know that Imin has to be smaller than Imax or equal to Imax. If Imin is equal to Imax, means we have one element in the array or one area to search for. But once Imin is greater than Imax, there's nothing to search for. So this entire thing is repeated in a loop. And finally, if we are out of the loop, we do not find the number, so we say return -1. So now, all we need to do is write the main. The main is going to be exactly same as the linear search main, so I'm just going to copy paste it here. Pasted the main from linear search. All we need to change is, instead of calling linear search, we're going to call binary search. The arguments that we pass are exactly the same. Now let's try and run this program. Let's compile it. No errors or warnings. Run. Enter number of numbers. Let's say 5. Enter the numbers. Now remember, for binary search to work, the numbers have to be in sorted order. And in this case, it has to be in ascending order. So let's give the numbers at 10, 15, 16, 30, 50. Now let's say I want to search for the number 10. Key found at position 1, which is correct. So our program works. And from theory, we know that the average case for the binary search is better than the average case for the linear search. Now we have seen two important search algorithms. Let's look at a few sort algorithms. Sorting algorithms are simple. The purpose of the sorting algorithm is to sort a given set of numbers. So we shall first look at something called the selection sort. The selection sort is very similar to how we as humans might try to sort numbers. Let's see how that works. So let's say I was given a set of numbers. I'm just going to take random numbers. If someone were to ask me to sort this, how would I go about doing it? If I were to sort it in ascending order, I would pick 10 is the smallest, so I would put 10 separately. Then I would see 15 is the next. Then I see 45. Then I see 50. And then I see 100. And it's sorted. So every given time, I pick the smallest number and store it separately. So that means I selected the smallest number and then copied it. This is why it's called selection sort, because at any given time you select the smallest or the largest, depending upon whether you're doing ascending or descending, and then store it separately. But in the selection sort algorithm, instead of storing it separately, we will store it within the same array. Because if you have to copy it separately, we need a new array. Instead of doing that, we store it within the same array. How do we do that? It's simple. So when I go through this list, I see 10 is the smallest. All I need to do is 10 being the smallest, it has to go into the beginning of the array. So I swap 10 and 45. So you get 10 over here, 15 stays here, 100, 50, 45. So now I'm sure this is 10, the position for 10, so I don't care about this. Next, I search from here onwards. I search for the smallest number starting from here. I know 15 is the smallest number, so I leave this as it is. Next, I start searching from here. Search for the smallest number, 45 is the smallest. So you swap 45 and the first number in this list, that's 100. So you get 45, 50, 100. Next, you start from here, then the right position, and you're done. And that's your sorted list. So let's see how do we write a program to do the same. As you can see the algorithm here too. It's simple. Find the smallest element on the list. Swap the element with the first element on the list. Repeat the same for the rest of the elements. So as usual, we start with hash include stdio.h. Now we're going to write the selection sort. The selection sort algorithm does not have to return anything to us, so it's going to be a void. Let's say selection sort. It's going to accept the array, and again we have to say from where to start sorting. So int imin and the ending of the array, so int imax. Okay, so the first thing we need to do is have a loop to go through every element. The logic is simple. At any given time, we start the loop from here. We see which is the best number which will fit in this position. We found that 10 fits in this position, we put it here. Next, we go to this position. We see which is the best number which will fit here. We know 15. Next, we go here. What is the best number that will fit here? We realize 45, and so on. So we need to have a for loop starting from the first position till the last position. At every given time, we need to find what is the smallest number left on the list and copy it to that position. So we have for I equal to I min, I is less than equal to I max, I plus plus. So I is keeping track of the positions. So I in the beginning starts from I min, which in our case mostly will be 0. So I is equal to 0. So now we need to see who will fit into the 0th position. For that we need to find the smallest number in the entire array. So let's have a function called smallest. So I'm just going to call a function smallest a comma I comma I max. So this function smallest takes the array a and finds the smallest number starting from index I until I max. So in the beginning, index I is 0, so it'll search for the smallest number from 0 to I max. Next time I will be 1, so it'll search from index 1 to I max, because at position 0 we already found the smallest number. Now we need to find the smallest number between index 1 and the maximum index. And next time it will be from index 2 to the maximum, and so on. So the function smallest will return the smallest number to us. In this case, we need the index of the smallest number, so we can swap it with the current position. So we say I small. So we need another integer. So once we have this, we need to swap it. So we say swap. If you remember, in one of the previous chapters, we had written a swap function where we had to pass the address of the two variables which we wanted to swap. So we can do the same here. Or a simpler way is, we already have a pointer, we pass the whole array, and we pass the index of the two areas that we want to swap. That's, we want to swap I with I small. And just to make it more efficient, we want to swap only if I and I small are not the same. So we can just say if I is not equal to I small, then we do the swap. And finally we end the for loop. So the whole for loop goes from I min to I max, and for every point we check which is the smallest number starting from that point, and we swap it. Now we need to write the two functions, which is smallest and swap. Let's start with smallest. Smallest has to return the smallest index to us. So int smallest takes the array, takes the starting index and the ending index. So let's say int small equal to I min. So we have for I equals I min plus 1, because we already have put the smallest index at I min. So you say I equal to I min plus 1. Actually, we are supposed to put a of I min. And plus 1, I is less than equal to I max, I plus plus. If small is greater than a of I, then small is equal to a of I. So if you can see, this program is very similar to find the largest number program we had written previously in one of the chapters. But in this case, we don't want to return the smallest number. We want to return the index where the smallest number is in the array. So instead of storing the number itself in the variable small, we're going to store only the index. So we can return the variable small, which will be the index. So here the check would be for a of small is greater than a of I, then small is equal to just I. And finally, once we're done with the whole for loop, we can just say return small. We have forgotten to declare I, so we can say int I. That's our function smallest. The other thing left is the function swap. It does not have to return anything, so void swap takes the array. It takes the two indexes to swap, so let's say int index 1 comma int index 2. Let's have int temp equal to ARR of index 1, ARR of index 1 is equal to ARR of index 2, ARR of index 2 is equal to temp. And we've swapped the two positions. So we're done with our swap 2. What's left? We just need a main. We're just going to copy the main from the previous programs because we have to again take in numbers. The only difference is we don't have to ask the user for a key. We have to just accept numbers from the user and then finally sort it. So let's just copy paste from the previous program. So we're done with this. Let's paste our main. All these things remain the same. How many numbers? Enter all the numbers. We don't need a key because we are sorting the numbers, we're not searching. Finally, our sort is not going to return anything. We just need to call selection sort, and we pass 3 arguments, that is the starting index, ending index, and the array itself. And finally, just to check if we've sorted it, we need to print the entire array. So we'll have a for loop again. So printf the sorted array for I equals 0, I less than num I plus plus, printf %d/n, we have ARR of I, and that's it. Let's save this program. Let's compile this program, and we have an error. The error says conflicting types for swap. This is because we had the function definition swap here, but we haven't declared the function. But if you remember, we also haven't declared a lot of other functions. This is because if you're using the function after the definition, it's fine. But if you're using the function before it's been defined, then it's a problem. So here, we're using the function smallest and swap, but it's being defined later. That means the compiler will not know what the parameters for the function are like. So we need to declare it. So let's have the declarations. int smallest, it takes an int star, int and int, and the void swap int star int int. Let's try compiling the program now. No errors or warnings. Can run it. Okay, how many numbers? We're going to say 5. We're going to enter the numbers. Let's just enter it in reverse order. So 5, 4, 3, 2, 1. This will be the worst case. The sorted list is 1, 2, 3, 4, 5. There you go. Let's try again with something else. 5 numbers. Just gonna enter 45, 1, 100, 20, 67. 1, 20, 45, 67, and 100. There, we have the sorted list. So this was one of the simplest sorting algorithms because very similar to how we as humans might try to sort numbers when it's given to us. Let's look at the next sorting algorithm. In this slide, we're going to talk about Quicksort. On average, Quicksort is faster than the previous sorting algorithms. The worst case in general is kind of similar to the other sorting algorithms, but on an average case, Quicksort is supposed to be faster. Let's take a look at how Quicksort works. The idea behind Quicksort is simple. You're given a set of numbers, so let's say 20, 10, 40, 5, 30. The idea behind Quicksort is to divide this entire array into two halves such that all the numbers in the right half are greater than all the numbers in the left half. By doing so, if we sort the right half separately and the left half separately, and you join the two halves, you don't have to do anything much after that. As soon as you join them, you still get a sorted array. So you want to divide this array in such a way such that all the numbers in the right half are greater than all the numbers in the left half. So how do we do that in case of a Quicksort? What we do is pick a number called the pivot number. It can be any number in the array. So in our algorithm, we would generally pick the first number. It's simpler. We just take the first number as the pivot. Let's call it P. Now we're going to perform the partitioning around the pivot number. That is, we need to find all the numbers less than 20 and move it to the left, and all the numbers greater than 20 will be moved to its right. Simple, right? So we're going to have two counters. We're going to have I starting from here and J starting from here. So all the numbers less than or equal to 20 should stay on the left hand side. So we will not do anything. But any number greater than 20 should move to the right side. So I will keep moving till we find a number which is greater than 20. Because 10 is less than 20, we don't need to do anything about it. It's already on the left hand side. But as soon as we find something which is greater than 20, it needs to be moved to the right side. So we keep moving I till we find a number greater than 20. This is not greater than 20. This is greater than 20, so I stops there. Similarly, all the numbers on the right side have to be greater than 20. So anything less than 20 will have to be moved to the left side. J is less than 20? No. So we move J to one step. 5 is less than 20? Yes. So now what we do is we swap these two positions. So 5 goes here and 40 goes here. So what you get is 20, 10, 5, 40, 30. This is our pivot, this is I, this is J. Once we've done this swap, we again continue the process. J needs to keep moving till we find a number that is less than 20. So J will stop here. Similarly, I needs to keep moving till it finds a number greater than 20. So I is going to stop here. Now I is greater than J, so we shall not swap these two, we will stop the process. Now all we need to do is swap J and our pivot P. This is because as soon as we do this, all the numbers to the left of our pivot 20 will be less than 20, and all the numbers to the right are greater than 20. As you can see here, 40 and 30 are greater than 20, 5 and 10 are less than 20. So all we need to do is insert 20 here, but because arrays, instead of inserting, we're going to swap. So you're going to have 5, 10, 20, 40, 30. So this was our pivot. So as you can see, all the numbers to the right of the pivot are greater than 20 and all the numbers to the left of the pivot are less than 20. Now that we're done with this, we can repeat the exact same process for the subarrays on the right and the subarrays on the left. So it's like a recursive call. For the entire array, we picked a random pivot number and then divided it such that all the numbers to the right are greater than it and all the numbers to the left are greater than it. Now that we're done with that division, we again continue the process for all the numbers to its right and all the numbers to its left. So when you repeat this process, automatically both the halves get sorted. This side is anyway sorted. This side also, what will happen is you repeat the process. You start with pivot over here, you start with I over here and j over here. You keep moving I till you find a number which is greater than the pivot, 40. This is greater than pivot, no, but it's the end of the array, so you can't move it anymore. You keep moving j till you find a number which is less than 40, which is here. Now again, I is not less than j, they were the same, so you don't do anything. All you do is swap the pivot and j. So you'll swap these two, so you'll get 30 here, 40 here. So automatically you've sorted this subarray. This subarray will also get sorted, or in this case already sorted, and you have 20 here. And you have the entire sorted array. Let us now see how we're going to write a program to do the same. As usual, we should start with hash include stdio.h. Now the first thing we're going to write is the partition algorithm. The partitioning is supposed to take care such that all the numbers on the right hand side are greater than all the numbers on the left hand side. So let's have a function called partition, which will take the array and it would take the min and the max. So for doing the partitioning, like we saw in the diagram, we need to first pick a pivot. So we shall have int pivot. As I had mentioned, we're going to pick the first number as a pivot itself. So pivot would be equal to a of I min. We then need our counters I and j. So we're going to say I equal to I min plus 1 starts from the next number and j is equal to I max. We need to declare I and j. So we've gotten all our counters in place. Now what we need to do is move I until we find a number which is greater than the pivot. So while a of I is less than pivot, but instead of checking against pivot, pivot is just going to have the index, and so we shall check a of pivot. This is required because we need to swap the pivot also later, so we need to know the position. So a of I is less than or equal to a of pivot. We do I plus plus. So as long as a of I is less than or equal to a of pivot, we just keep incrementing I. As soon as we find a number which is greater than the pivot, we stop. So I is pointing to that. Also, we'll make sure that I doesn't go across the boundary. So we'll just say and I is less than I max. This is to just make sure we do not go beyond the boundary of the array. Similarly, we need to keep decrementing j. So while a of j is greater than a of pivot, we do j minus minus. So j stopped as soon as it finds a number which is less than the pivot. So now we have both I and j. All we need to do is, if I is less than j, we need to swap the two numbers. So if I is less than j, we say swap a comma I comma j. Now if I is not less than j, what do we need to do? That means we're done finding the right position for the pivot. So all the numbers to the right hand side are greater and all the numbers to the left hand side are smaller. All we need to do is swap the pivot with the jth position. So you say swap a comma pivot comma j, and we're finally going to return the position of the pivot, which is the jth position. So now that we've done the swap, the pivot number has gone to the position j. So which is returning the position where the pivot has moved, which is return j. So the partitioning has happened on both sides of the pivot. On the right hand side of j, all the numbers are greater than the pivot. On the left hand side of j, all the numbers are smaller than the pivot. So the function partition is basically going to partition the array and return the index where the partition has happened. So we're returning j. So this is simple. Now if I is less than j, we swap, but the algorithm doesn't end there. We need to continue again. Again, we need to move I forward and j backward, and this needs to go on till I becomes greater than j. So all we need to do is have this entire thing in a loop while 1 . So all this goes into the loop. So this is an infinite loop, but it doesn't matter to us because we need to keep repeating I and j as long as I and j are. This is an infinite loop, but it doesn't matter to us because we need to keep incrementing I and decrementing j until I is greater than j. So once I is greater than j, we swap j with the pivot and then return from the function. So we won't actually get stuck in this infinite loop because we're going to return out of the function over here. So we have our partition function. Now we're going to actually write the quicksort function. So we have a void quicksort in star a comma int imin comma int imax. We need to actually sort the algorithm only if imin is less than imax. So if imin is less than imax, what do? We first have to partition it. So we say partition a comma imin comma imax. Now the function partition will return the index across which it was partitioned. So let's say j equal to partition. So now we know all the numbers to the right hand side of j are greater than j and all the numbers to the left hand side of j are smaller than j. But that does not mean the numbers to the right half and the left half are sorted. We just know they're greater or smaller, but they haven't been sorted yet. So we need to sort those two using the same method. So we're going to call quicksort again. Quicksort a comma. Now we need to sort the left hand side separately, which is imin comma j minus 1. Because j is in the right position, we don't need to worry about where the jth element is. It is in the right position in the array. So we sort the left hand side of j and the right hand side. Quicksort a comma j plus 1 comma imax. So this one sorts all the elements from beginning until j, and this one sorts all the elements from after j until the end of the array. Now we're done with the quicksort algorithm too. Let's copy and paste the swap and the main. As these two don't change, we just can declare it. There. Let's try and compile this program. We have an error. This is undefined reference to bubble sort. Oh yes, we forgot to change the main, we need to call Quicksort now. Let's compile it again. Let's run the program. Enter let's say 5 numbers. I'm going to enter them in reverse order, and it works. Let's try again. How many numbers? 5 again. I'm just going to enter them in the sorted order itself, and it works again. Now let's try some random set of numbers. 5 numbers. I'm just going to say 12, 50, 32, 1, 15, 1, 12, 13, 32, 50. And as a last try, we can just try some numbers which repeat themselves. So we say 10, 20, 10, 30, 10. And that's sorted too. So this is our quicksort algorithm. Let's just take a quick walkthrough. It's simple. All we're doing here is making sure imin is less than imax, because like I said, for every recursive function, we need to have an ending point. In this case, as soon as imin becomes greater than imax, we will quit the recursive function. Until then, if imin is less than imax, we first find the partition. So what partition actually does is picks a random pivot number. In this case, it takes the first element as a pivot number, and then it partitions it in such a way so that all the numbers to the right side of the pivot are greater than the pivot, and all the numbers to the left hand side of the pivot are less than the pivot. So that's what this entire while loop does. As explained in the diagram, we keep incrementing I, decrementing j, and then swap I and j, and finally we swap the pivot and j. So your partition makes sure that once we return j, all the elements to the right hand side of j are greater than the element at j, and all the elements to the left hand side of j are lesser than or smaller than the element at j. So we completed the partitioning and we returned the index where the pivot element is. Now once we know that j has been partitioned correctly, that means the element at j is in the right position. So once we sort the entire array, whatever element was at j, it does not have to change its position because we found the right spot for that particular number. All we need to do is sort the left hand side of this and the right hand side of it separately. So now we say quicksort again for the left hand side, that's imin to j minus 1, and for the right hand side, that's j plus 1 to imax. So that is our quicksort algorithm. So finally, in this chapter, you've learned the various search and sort algorithms, and you've also learned the advantages or disadvantages of using these algorithms.